in exercise 1C, we will talk about backpropagation and the gradient descent algorithm. So first, we will explain how gradient backpropagation works for the MLP with 2 hidden layers, and then we'll talk about how gradient descent works in combination with mini-batch training. Okay, so let's write down the model equation of a neural network with 2 hidden layers. So on the left side, I write the output as always. And now let's think about it. What would be the input for the first hidden layer? So not the first neuron, but the whole layer. And this would be the matrix of weights times the inputs, which I call X this time. You could also call it I, as we did in the lecture, but doesn't matter right now. And then add a vector of bias to it. Okay? So when we had the single neuron, then we would do this just with a vector of weights that we would multiply with the inputs, add it up basically, and add the bias term. And as we have the whole vector and the whole hidden layer, we would do this for many neurons, and there would this way we would have not a vector of weights but a matrix of weights. Okay, and then we apply the activation function to all the outputs of the whole layer, so not only one knot but all the knots. And then we have basically our inputs for the next hidden layer, which we will multiply with the weight matrix of the or associated with the next hidden layer. So weights times inputs, and add a bias. And now we will have the inputs for the output. Or first of all, we have to pass this to a activation function of the second hidden layer. And now we can pass this to the output, and the output has a weight matrix itself, and we add the biases for the output. And now if this is a single neuron output, which would mean that not a single neuron out, if this is a classification, then we would need to apply another activation function here. If it wasn't a classification but a regression, we could just leave it without the last activation function, then it wouldn't need an activation function. So, but as I told you in the exercise before, we would need a sigmoid activation function, for example, for binary classification, or softmax for multi-class classification. Okay, so this is the MLP with two hidden layers. So, and now you can see how this is, or the structure is basically onion-like, so a multi-layered structure. Okay, so now if we, or the model, not of multiplication, but of its multiple layers of activation functions applied to matrix multiplication. Okay, and this way we have this onion-like structure. Now we want to minimize our loss function, as we always do, because this will generate the best fit of our model. So we minimize over the weights and the bias. So basically we could also put little indices here so we know these are different matrices and or vectors in these cases. And now our our loss function is defined, for example, by this sum of squared residual function. And so you know this already. And now we want to minimize this, but we can't minimize it as we have done before. We need to have another approach, which will be gradient descent. And to apply gradient descent, we need to first apply backpropagation, or basically in combination, which is just the chain rule applied. So we get the weights, and then the gradient descent algorithm will subtract these weights from the, or not these weights, the partial derivative of the weights to update the weights. Okay, so first we get the partial derivatives. And we need the chain rule so we can calculate the partial derivatives within all these functions. And the deeper we get, the longer the partial derivative term will be, because basically we have to apply another chain rule for every function we go into. And there you can see the notation of that, how it's done in the lecture. The professor already explained that. And if we have these partial derivatives, then we can apply the gradient descent algorithm and update them. And by subtracting the weights, not the weights, by subtracting the partial derivatives from the weights, we will reduce the total error. Because we can basically say that the partial derivative is how much does this weight contribute, the single weight contribute to the error. And if it's a high contribution, that means that the partial derivative is very high, then we must reduce this weight, because this weight had a lot of say, let's say, in the wrong classification, for example, or in the high error. And as we want to minimize the error, that's bad. So if it basically had a lot of say in that, then we have to reduce it so it will be not that important next time. And if we do this over all weights, then this will get us closer and closer to the true classification, or to the true value. Okay, because by subtracting the partial derivative, or let's maybe note down first the equation of the gradient descent algorithm. So that's just the weight of the next pass, or for the next pass, will be the weights minus learning rate times the partial derivative. So pretty easy. There are also different variations for the gradient descent algorithm, but we won't go into detail. And this learning rate is normally between 0 and 1 because it has to reduce the partial derivative. Otherwise, we could overshoot at times, and we don't want to do that. We want to have like this slow progression, slow but steady progression towards our minimum of the loss function. Okay, so if you think about that, this amount of say, let's say, the weight had or the impact the weight had on the error was high and the error was high, then we want to reduce the weight that we talk about because that led to the wrong classification or to the high error at least. And this we do by subtracting it from the weight. So let's say the weight is 10 and then this partial derivative is 1. Then we would subtract it, but we won't but let's say the learning rate is 0.5, then we would only subtract 0.5, then it won't then the weight will be smaller, and by adjusting all the weights this way, this would lead us to a better classification. Also, if it would be very positive and maybe this derivative would be even negative, because this weight was responsible in a reduction of the error, then this would be basically positive. So it would be this weight, the old weight plus the derivative, and this way the weight would be bigger, and this positive classification or positive influence on the weight on the error would be enforced for the next time. Okay, this is how the weights will be adjusted, and we will do this for every, like, it depends on now which kind of learning you use, because when do we want to apply this gradient descent algorithm? Do we want to apply this after every observation, or do we want to apply this after all the observations? And so if we would apply this after every observation, we would have to calculate the derivatives after every observation, calculate the gradient descent, add it up, and so on. But what we tend to do is we would use mini-batch training, which means that we slice our whole data set into subsets of the same size, maybe 40 observations, and then we would train our network on these 40 observations, calculate the derivatives for the losses. So for every loss we would make a prediction for one observation, then we would calculate the loss, then we could calculate derivatives, would make the next one, and so on. And after the whole batch of 40 observations, then we would apply the gradient descent algorithm for all the observations in this batch, and this would look the following. So for mini batch training, so the weight of the next period would be the weight, so this should be also matrices of the current period, and then we subtract the learning rate, and then calculate the derivatives. Then we use the average of the errors. So instead of the error from one observation, we will do this for the errors of all the observations in the batch. So the average error over the batch. And also the loss function would have another form. So for mini batch training, you would then have this loss for every batch. Okay, but basically we update the mini batch training. I didn't know if I said it correctly, by having the old weights before this batch, or this weight J we used for the calculations within this batch. For all the prognosis we used WJ, and then we make our predictions with the model for all the observations in this batch, calculate the respective 40 errors from that, and calculate our derivative, and then we update the whole thing for the whole mini batch in one go by and we use the average of all the errors for that.